We left off in class talking about acetal formation, so let's pick up where we left off. So the overall reaction for acetal formation is the reaction of an aldehyde or ketone with some kind of alcohol. This is done in the presence of an acid catalyst, and the resulting products, which are these geminal alkoxy compounds, are called acetals. One of the byproducts of the reaction is water, and as we'll see a little bit later, that's actually kind of useful. So as an example reaction, we see here the reaction of cyclohexanone with methanol. Our catalyst is an organic derivative of sulfuric acid, basically just sulfuric acid where one of the hydroxyl groups has been replaced by this toluyl group. It's called para-toluene sulfonic acid, or tosic acid for short, and you'll see it abbreviated like this. And this is something we'll see commonly in a lot of our acid-catalyzed reactions. So let's jump right into the mechanism, and then we'll talk about some of the particulars of the reaction. So the overall balanced equation is what we see here. In this example, we have acetone reacting with methanol. It takes two equivalents of methanol. Our catalyst is neither consumed nor destroyed in the reaction, so you'll see it appearing here. Sometimes you'll see that written in square brackets. And here is our dimethyl acetal of acetone and our water product. So let's draw out the mechanism of that reaction. So reaction begins with acetone. Basically, every step in the mechanism is in equilibrium. When we add para-toluene sulfonic acid to our methanol solution, some of the methanol is protonated. So this is analogous to hydronium ion. This is basically a derivative, a protonated version of the alcohol. This is our proton source in the reaction. So mechanism is analogous to acid-catalyzed hydration. So the first step in the mechanism is protonation of a carbonyl, which produces this oxonium ion. What that does is convert the weakly electrophilic acetone into now the strongly electrophilic protonated acetone. Once protonated, then methanol will add, even though methanol is a weak nucleophile, like so. Produces this oxonium ion intermediate. Which, on transfer of a proton back to the solvent, leads to this intermediate. So that intermediate actually has a name. This is called a hemiacetal. Essentially means half an acetal. So that part of the mechanism looks like hydration. So if you replace the methanol here with water, you'd end up with the hydrate. But with alcohols, the reaction continues. Next thing that happens is another protonation. But this time the hydroxyl group is protonated. Like so. So what that does is convert the hydroxyl group into a very good leaving group. And the molecule undergoes elimination. intramolecularly, like so. That step is generally kind of non-reversible. And the reason is, if we draw out the products, you can kind of see why. That we lose water. So that's a key feature of the reaction, the loss of water. The other thing to note is how similar this species is to our protonated acetone. So if you look at our protonated acetone up here, you'll notice it's highly electrophilic, methanol added to that quite readily. This is isoelectronic with that, so it should be every bit as electrophilic. And in fact, it undergoes the same nucleophilic addition. Like so. So the product that addition is that oxonium ion, and then one final proton transfer, regenerating our catalyst, by the way. Like so. And we have an acetal. So there's our overall acid-catalyzed formation of an acetal mechanism. Let's talk about some of the other details of this reaction. So first off, why is acetal formation catalyzed only by acid? The reaction actually doesn't work in base. So if you think about it, and what mechanistically should be taking place, under basic conditions, our alcohol should be deprotonated so that we have some alkoxide ion. This is analogous to hydration under basic conditions where we have hydroxide ion. Well, that's fine. Alkoxide ion is a strong nucleophile, should add readily to our carbonyl. That would lead to this structure. So this is the alkoxide, negative charge here, and that can be protonated by more of the alcohol, which gets us to the hemiacetal. But now we have a problem. In order for the hemiacetal to react further and become an acetal, somehow or another we need to get rid of this hydroxyl group. And under basic conditions, we can't get rid of it. The alkoxide is not a strong enough nucleophile to react. Hydroxide is such a poor leaving group that it won't undergo direct substitution. It won't undergo elimination because it's a poor leaving group. And so basically we get to an endpoint. So under basic conditions, alcohols will react, but they'll only lead to an equilibrium mixture that has some hemiacetal in it, and that reverts back to the ketone. So you can't make a full acetal under basic conditions. Generally, we find that the equilibrium constants to these reactions differ based on the structure of the starting materials, and this is for the same reasons we talked about with hydration. So, for instance, simple aldehydes reacting with alcohols generally have quite favorable equilibrium constants, and at equilibrium you can isolate a fairly large amount of the corresponding acetal, 50% or more. On the other hand, ketones or hindered aldehydes generally have equilibrium constants that lie to the left. We get steric strain, when we first convert to the acetal, the carbon is sp3 hybridized. Also, the starting ketones are more stable than starting aldehydes. So we're seeing the same kind of effects that we saw with hydration here in the acetal formation. But there is a workaround. There is a way to drive the reaction to completion. And the way to drive the reaction to completion is to take advantage of the byproduct of the reaction, which is water. So if we could remove the water from the equilibrium, then the reaction should be driven forward. And this is commonly done by what's known as azeotropic removal of water. So you can do this by taking an aldehyde or ketone, an excess of the alcohol, a catalyst in the usual way. But then what you do is you add some solvent to the mixture. The solvent might be, for instance, it has to be something that forms an azeotrope with water. One of the more common solvents that's used is toluene. Toluene famously forms a very good azeotrope with water. An azeotrope is a binary mixture of water in the compound. Benzene does the same thing. Benzene is a little more hazardous than toluene. And so by doing this, what we do is we take advantage of the fact that the byproduct of this overreaction is water, but we are in effect removing the water from the reaction. And Le Chatelier's principle says if we can remove the water, we're going to drive the reaction forward. And so this is very commonly done in the lab. Just like hydration and some of the other reactions we talk about, these reactions are reversible. And in this case, they're reversible primarily based on the conditions that you use. So if you run the reaction with an acid catalyst but an excess of water, you're going to drive that equilibrium toward the carbonyl compound. If you have an excess of alcohol, you'll drive the equilibrium toward the acetal. So once you have an acetal, if you want to convert it back into its carbonyl form, you simply add a lot of water in an acid catalyst and it's converted back. Now, I'm going to leave it up to you as a little exercise while you're studying is for you to write a mechanism for this reaction. You should be able to do that. So the reverse mechanism of the acetal formation. Now remember, halfway through our mechanism, we got to a structure called a hemiacetal. Normally hemiacetals can't be isolated if they're acyclic, but there are scenarios where they can be isolated and they're actually quite stable. These compounds that you see here exist largely in the form of their hemiacetals. So you'll notice this little 1, 2, 3, 4 carbon aldehyde alcohol. This alcohol moiety can react intramolecularly with the carbonyl and form this intramolecular hemiacetal. And in fact, that's a quite stable structure, such that this compound exists in pure form as roughly 89% hemiacetal and 11% open chain. The 6-membered ring is even more stable than the 5-membered ring, and so this little compound over here also reacts intramolecularly and forms this hemiacetal, and it makes up 94% of the compound at room temperature. This is really important in biological systems because there are a lot of biological molecules, carbohydrates specifically, that have within them carbonyl functional groups. This is glucose, and it has at one end of this carbon chain an aldehyde, and then you'll notice a bunch of alcohol groups. And glucose predominantly exists as a hemiacetal form, where this alcohol at this position reacts with the carbonyl and forms a 1, 2, 3, 4, 5, 6-membered ring. And so glucose, for all intents and purposes, is that. We also find the hemiacetal groups present in more complex carbohydrates. This is lactose, the sugar that appears in milk. Some people are somewhat intolerant of lactose. They don't have the proper enzymes in their gut to digest it. And it exists both as an acetal. You notice the structure here. You got the two oxygens attached to the carbon. That's an acetal. And a hemiacetal within the same molecule. When you go on to study biochemistry, you'll talk more about the structures of these sorts of compounds. We can make cyclic acetals in the lab by using diols of either 2 or 3 carbon chains. Ethylene glycol, which is this compound here, reacts quite readily with aldehydes and ketones. If you do this under azeotropic conditions where you move the water, you can drive that reaction forward. And this one molecule provides the 2 hydroxyls that react with the carbonyl compound to form the acetal. Thiol groups are structurally and electronically very similar to alcohols, and so thiols will react with aldehydes and ketones and form very similar structures. These are called dithiones, and these have a lot of different uses in the laboratory. These reactions are even more favorable, as it turns out. The equilibrium constants tend to be greater. So here's another study exercise that I want you to do. I want you to write mechanisms for both these reactions. To finish this section, I want you to know that some of us actually do the chemistry that we talk about in these lectures. And the 2 reactions that you see here are reactions that you can actually find in my dissertation. You're welcome to come by my office and take a look if you'd like. But these were reactions that were part of the synthetic work that I did on the molecule amphotericin B. You can see it down here. This was a long time ago. In this case, I had synthesized this particular compound here with these 2 hydroxyl groups in it previously. It was a chiral compound. I needed to do some subsequent chemistry where these alcohol groups were going to interfere, and so I used this as the diol, reacting it with acetone, to form this cyclic acetal. I also had the occasion to form a dithione, again for reasons I won't go into. And I did that reaction by reacting this aldehyde, which actually was derived from this compound up here, reacting this aldehyde with this 1,3 dithione. And by the way, I hope you never have to work with this because it smells like skunks. And this reacts quite readily. I used a Lewis acid rather than a protic acid in this reaction, again for reasons I won't go into, and it very clearly formed these dithiones. By the way, when you're doing graduate work, your yields have to be quite high. All right, that's the end of this section. Please go on and watch the next lecture from this chapter.